Okay, now let's look at compound statement. We are going to see what the meaning of this compound statement when two propositions are combined, one or two propositions are combined by this logic operations. Let's use P to denote the proposition that FIU is a public university, and the Q, we use Q to denote proposition that FIU is a university located in Miami. First of all, what are the proposition not P means? Okay, that means FIU is not a public university. I guess that equivalently, this means FIU is a private university. If I'm not wrong, so the university is either public. Every university is either public or private, and of course not Q. That means FIU is a university not located in Miami. Okay, so what does P and the Q mean? What is the proposition of P and Q? That means FIU is a public university and FIU is a university located in Miami. Okay, we can write this more compactly as FIU is public university and located in Miami. It doesn't matter the statement is true or false. We just want to understand what what kind of proposition we are going to get if we combine two proposition using this logic operations. And the next one is P or Q. By the way, P and Q, FIU is public university and located in Miami. This statement is true if and only if both P and Q are true. That means P and Q is true if if P is true and Q is true, and is false if one of them is false or both of them are false. And what about F or Q? The statement is FIU is a public university or located in Miami. And this statement is true if either P is Q, sorry, P, I'm going to write this, P is true if and only if P is true or Q is true. Or both. Both are true. And of course, P and Q is true if and only if both P and Q are true. Okay, I think you shouldn't have any difficulty in understanding these three logic operators. I think maybe you have some difficulty in understanding this exclusive OR. This means it's called exclusive OR because it's very similar to OR. It's almost the same as OR, but the only difference is this is true Compound statement should be if FIU is a public university or is located in Miami. Sorry. But not both. So P exclusive or Q is true if and only if exactly one of P and Q is true. So if both P and Q are true, is P exclusive OR is false. So you may wonder why we care such operations. We are going to see that this exclusive OR is very useful. But at this moment, let me give an example. Suppose FIU can get a grant if this P and Q, P XOR Q is true, just because it can get a grant if it's a public university. If it can get a grant if it's one university in Miami. But because there is already a university, a public university in Miami already get a grant, and they can only fund one public university in each city. So that means if you meet both conditions, if you are a public university in Miami, you cannot get a grant. Okay, and I guess you can easily construct many examples by yourself. Let's move on to next topic. Next topic is we are going to discuss what is a truth table. And truth table is a very, very important notion, very useful tool for verifying logic equations. So what is the truth table? Truth table is because for each proposition, it can take only two truth value, either true or false. And if I have P and Q, so there are only 4 possibilities for P and Q. So because P and Q can be true, 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 false, false, true, false, false. There are only 4 possibilities. And if we consider all these 4 possibilities and we list all the truth value of their compound statement, we have a good idea of what's the truth value, what the truth value of the atomic proposition, what the relation between atomic proposition P and Q and the compound proposition. For example, P and Q, P or Q, or P XOR Q. Okay, so let's start from this simplest one. So P. So in truth table, we usually we write this propositions as a column. Okay, and so this is not a P. So P can, there are 2 possibilities. P can either be true or false. So this is very generic. It doesn't have this applied for any proposition. So we don't need to worry about, we don't need to plug in any statement for this relation. It's applied to anyone. So if P is true, we know that not P is false. So because this is the definition of not. Okay, if P is false, and that means not P is true. Okay, very simple. And what about P and Q? So we are going to list P and Q, and then the third column is P and Q. So remember, we have 4 possibilities. If P can be true, Q can be true at the same time. And when P is true, and Q can be false. And the third possibility is P is false, and Q is true. And the last possibility is P is false and Q is also false. So there are only these 4 possibilities. And this is just because for each proposition, there are only 2 possibilities, either true or false. And this makes things much, much nice and simple. So what is a P and Q when P and Q are both true? By definition, we know it's true. Okay, if P is true and Q is false, remember P and Q is true if and only if both are true. So this means because Q is false, and this is false. And next one is false. And the last one, because both are false, is also false. Okay. So now we are ready to extend this this truth table. This is called the truth table. Okay, let's extend this truth table to consider P more compound propositions, P or Q. And you can easily see that this is true when P and Q are both true. If P and Q, one is true, is true. So this is true, and the last one is false. And what about next one, P XOR Q? And this one, remember, the only difference between this and the P or Q is if both are true, this is a false. So this is a false, this is true, this is true, and this is false. Okay. So what about P implies Q? This is a little bit tricky. So for some reason we are going to see later, we consider this to be true automatically. We say it's true by default if the premise P is false. Okay, so this P implies Q means if P is true, then Q. So it doesn't say what happened if P is not true, and we are going to see it make perfect sense if we define if P is not true, this automatically is true. So we are going to have this is true, and so P is true, Q is true. So that means if P, then Q. This is true. This is right. And next one, if P, then Q. This is false because the premise is satisfied. P is true, but Q is still false. So this is false. And similarly, Q implies P. And this is true. Sorry, this is true, and this is true by default, and this is false because Q is true, but P is false. Okay, the last one is P, and P implies Q, and Q implies P. So what does this mean? It's the same as P and Q. P implies Q, and Q implies P. So therefore, we just need to end these 2 columns. Okay, TT and ST. FT is false. T and F is false. TT is true. And so now you can see it make perfect sense. Why? Because so when P and remember we say P implies Q and Q implies P means P and Q are equivalent. So we know that in the first row they're equal, so this is true. And in the second row, P is true, Q is false, so this is false. So that means P and Q are not equal. The third row is P is true and Q is P is false, Q is true, and they are not equal. And the last one, both are false, they are equal. So That makes perfect sense. This is just a P equals Q. P and Q are equivalent. Okay. So the next topic we are going to discuss. Let's move to the next slide. So we are going to define what logical definition, equivalence definition. Logical equivalence. Equivalent. So we say two propositional forms. Positional forms said to be logical equivalent if they have the same truth table. Okay, and this is very important because sometimes you have very complicated logical expression, and maybe this logical expression can be simplified to a very simple one. And you want to show that these two are equivalent. How can you show that? And you just simply show that they have the same truth table. Let me give you an example. I want you to show that P inclusive all Q is equivalent to, say, P all Q and P and Q, the negation of this. Okay, first, if you look at this, it seems to make perfect sense, right? Because what the difference between P exclusive all Q and the P all Q? The only difference is you want to make sure that you are going to return false when you have this P and Q are both true. Okay, so you can see that this expression is trying to do that. So we first have OR operation, and we end something which is false if both P and Q are true. Okay, so let's. It's intuitively this should be right, but how can we formally prove this? We can prove this easily by a truth table. So what we are going to do is we create a truth table P and Q. Okay. So very simple. We have only 4 possibilities: TT, TF, FT, FF. There are only 4 possibilities. Okay. And because the right logic form involve POQ, so we first write POQ. And now I want to give this POQ a special name. I call it X. Okay. And so that, and then we are going to have this P and Q. I'm going to give a special name Y. And so to let you see clearly what we are doing, I'm going to then we do negation because we have this P and Q negation of P and Q. So I will call this Z. And so what on the right hand side is P all Q and not of P and Q. And by our notation, this is nothing but X and Z. And finally, we have P and Q. And to save some time, we are going to run very quickly for this because we have seen this before. And so this is a TF, and this is TF, F, F. Please make sure that you can do this by yourself. It is very basic, and we are not doing anything fancy. This Z is negation of P and Q, so just negation of the previous column. So is F, T, T, T. And now I want to end these two columns, and we are going to see this is F, this is T, this is T, and this is F. Okay. And what is P plus Q? Remember, P plus Q is this is F because both are true, and the one is true, true, both are false is false. So then we're done. Why? Because you can see this one equal this one, these two last columns are just equivalent. And so we're done, and then we place this special symbol, this black square to denote end of proof. And sometimes it's called QED. Okay, let's see another example. Let's call this example 1. So next example. The next example I'm going to show you is, I guess, probably you can see easily. What is the equivalent form of P? P implies Q. Remember P implies Q. I'm going to use this table. So what is a P implies Q? Remember P implies Q automatically is true by default if P is false. So this is true. The last two rows are true. And the first row is true also because both are true. And the second row is false. P implies Q. So what is this equivalent to? I think it's very easy to check. So this is not P or Q. So if P is true, if P is false, then automatically it's true. Okay, because this is by default. So we first have this not P, which is true when P is false. If P is true, then you have to make sure Q is true. And then because you have this not P, this is false. So you can see that P implies Q to true in false, Q must be true. So we have this equivalence. And similarly, what about not P implies Q? Not P implies Q, and so not P implies Q. It's just negation of the previous column. So this is a false, this is true, this is a false, this is a false. And you can see that, and this it's easily can be verified is a P and not Q. What we want to say is this is not equivalent to. Okay, so what is P implies not Q? P implies Q, not Q is just by our first row, by this one, is equivalent to not P or not Q. Okay, so you can see that this is a P, not of P, negation of P implies Q is a P and not Q. And then P implies not Q is equivalent to not P or not Q. So these two are different. And that means, so if P, then Q. So what is the negation of this? It's not, this is a caveat. It's not if P, then not Q. It's very important. Okay.